All right, we're continuing with number one off of the uh, last minute review, part two, and we're looking at part L. It says m of x is defined as f prime times g prime of x over 2. We want to find m prime of 6. We want to find the derivative of this expression, and here we see that our equation is defined as two expressions being multiplied together. So we're going to have to step through product rule. And so f prime, which is a derivative of this first expression, so f prime turns into f double prime. The original g expression stays. Back to f, original f. And then g prime, the derivative of this expression. Notice that there's something inside the parentheses, so we have to go through chain rule here. So g prime turns into g double prime, and then x over 2 turns into 1/2, or 1/2 x becomes 1/2. All right, now we have everything spelled out for our derivative. Replace every x with 6, and then we clean up. So f double prime of 6. This is the f prime graph here. So f double prime of 6. What's the slope of the graph? Sorry, what's the slope of the graph at 6? That's going to be 0. So 0 times g prime of 3. That's just going to be 0 overall. And then 2 times g double prime of 3. G double prime of 3. That's just the table of values here. So g double prime of 3 is going to be -1. So 2 times -1 times 1/2. That cleans up to be just -1. Next part here, evaluate the definite integral of this expression to g triple prime of x plus 7. We're going to have to separate this into, let's separate this into two problems so we can kind of take care of these independently from each other. So I have 2g third g triple prime of x dx from -1 to 3. And then the definite integral of 7 from -1 to 3. This we can go through first theorem. We know g triple prime will just move up a degree to g prime. No need for u substitution. There's nothing here except an x inside. But this 7 here, we can go through power rule. So 7 becomes 7x, plug in upper bound minus lower bound. So here, after we make this turn into its antiderivative, we can then evaluate the bounds. So plug in 3 and plug in -1. So we have second derivative at 3, second derivative at -1 with coefficient of 2. That's going to tag along to both terms. And then here we have 7 times 3 plus 7. And we make all this come together. G double prime of 3. It's just a table of values, which is going to be -1, and g double prime of -1 is just going to be 10. We're just pulling the values from our table here. And then just combine all these terms to get positive 6. All right, next part here. If the definite integral of f prime of x is equal to 5 minus 2 pi, then find the definite integral from -2 to -6 of f prime. So let's see here. We have -6 to 2 defined, but notice that -6 to 2 includes a region that we don't see on the graph. So it's kind of like an unknown here. And there's an unknown plus -2 to 2. All that is going to add up to to be this value here, okay, 5 minus 2 pi. But we want to find the region that we can't see, this definite integral from -2 to -6. Now let's establish an equation that represents, that connects all these integral expressions together. So what if we take this part that the problem gives us, -6 to 2, that's a pretty large region here. What if we split this up into unknown portion plus a portion that we can find out, which is known? So let's split them up. We know that this full region from -6 to -2, we're going to break it up into two regions from -6 to -2, and then from -2 to 2. This is the part that we can't see on the graph. This part we can see, so we can figure out, but just by totaling the regions using geometric formulas. So the definite integral from -2 to 2 that's just going to be this whole this region here that I highlighted by shading in. Now this is not going to be a shape that we can recognize, but we can think of it as a combination of two shapes here. We can think of it as a rectangle and then just removing the semicircle. So if I take a rectangle and if I remove the semicircle, then I'm left with that these leftover regions. So rectangle minus semicircle, 8 minus 2 pi, and that we can represent that as this portion here. Now we know this portion is given to us is 5 minus 2 pi. Unknown will stay unknown for now, and then we can represent this rectangle minus semicircle as 8 minus 2 pi. So what if we just combine all this together, and then we can get this by itself. So subtract the 8, add the 2 pi over. The 2 pi's cancel out. I'm left with negative 3. So the definite integral from negative 6 to negative 2 of f prime is equal to negative 3. Now this is close, but it's not quite exact what the problem is asking for. It's asking for negative 2 to negative 6, which is just the same thing, just the bounds are flipped. So if I want to get this to match this expression, I'm going to have to flip the bounds. When I flip the bounds, I have to change the sign so I can make a balance there. So my negative 3 is going to turn into a positive 3. Next part, when I see a complex limit problem like this, I'm thinking this is probably going to be an adaptation of applying L'Hopital's rule. But first, we have to look to see what we get with the limit. So I'm going to evaluate the limit of the numerator. So definite integral from 4 to 2 of f prime. 4 to 2, I'm going backwards here. 4 to 2 is here. Sorry. 4 to 2 is here. This is a positive 2, but 4 to 2 is going to have to change the sign, so we're going to make that a negative 2. So negative 2 plus 2 is just going to be 0, so the numerator produces 0. The denominator, evaluate the limit of the expression below. If we plug 2 in for x, we get sine of 4 minus 4, which is 0. Numerator produces 0, denominator produces 0, so now we're going to go through L'Hopital's rule. So L'Hopital's rule, we take the expression, we force it through the derivative process. So the derivative of this expression is going to turn itself just into derivative integral will cancel each other out. This will turn into f prime of x. X becomes 1, and then sine becomes cosine of u times u prime. So cosine of x squared minus 4 times 2x. We reevaluate in the hopes that this will produce a real number, and we get f prime of 2 plus 1. F prime of 2, we look at our graph. F prime of 2 is just equal to 2. So 2 plus 1 is 3. Cosine of 4 minus 4, that's 0 times 4. Sorry, cosine of 0 is 1. 1 times 4 is 4, so 3 over 4. All right, last page for this extended number 1. Is there a time c between negative 4 and 3 such that g double prime of c is equal to 0? We have g double prime in front of us, so there's no need to find the derivative. This is really just, does this location, this y value, going to exist on the g double prime graph? And we have a bunch of values here, and we know that we can kind of go through IVT. All right? If we're trying to look for a particular point on the graph and we have other points on the graph, let's just look to see how often, whether the endpoints produces a value below and above. If it does, then it has to cross through that y value somewhere between. So first thing we have to establish is the function continuous, and it is. G double prime is given to us as a continuous function. Well, it says differentiable, but if it's differentiable, then you can make the claim that it's also continuous. So we know that g double, let's see, the endpoints here, we need one endpoint to be above 0 and the other to be below 0. So negative 4, g prime of negative 4 is 13. That's obviously above 0. So we're starting at a point above 0, and then at 3, it's going to dip down to negative 1. So it's going to go from 13 to negative 1, And if it goes from 13 to negative 1, it has to cross through 0 if the function is continuous. So we can guarantee that between negative 4 and 3, there must at least be one time t c value where g double prime is equal to 0 on the interval from negative 4 to 3. For next part here, for negative 6 to negative 2, we have f prime defined here. If f of negative 2 is equal to 0, find the minimum value. So if we want to find the minimum value on the closed interval, we have to apply extreme value theorem. So extreme value theorem means we're going to test endpoints and we're going to test critical points. Okay. So we're going all the way to positive 2 here. So we know we have to test negative 6. We have to test critical point, and we have to test 2. So I think I need to make the change there. That should read a 2. So we know we test the endpoints, which is negative 6 and 2. But to find the critical point, we're going to set this f prime equal to 0. So set f prime equal to 0. I can multiply both sides by 4, take the cube root of both sides, and we get x equals negative 4. Okay. So negative 4 is a critical point where f prime is equal to 0. So we're going to test negative 6, negative 4, and 2. So to find f of negative 6, we're going to start off with a point that is known and which is given, and add on that displacement. So the depth integral from negative 2 to negative 6, I see that initially my bounds are backwards, so I'm going to flip it and change the sign. And then I can go through or use my calculator for my f prime. Since this is not on the graph, I'm given this f prime here. And so we're going to be plugging this into the calculator, and this will give us 0. So this is 0, that's 0, and we get total of 0. F of negative 4, okay, which is the value here. We start at negative 2, we go from negative 2 to negative 4, and this is also going to produce, well, this will produce a negative 1 if we plug in the calculator. So 0 minus 1 is negative 1. And then finally f of 2 is f of negative 2 plus depth integral from negative 2 to 2, which is this 8 minus 2 pi. This is the portion that we can see on the graph. Okay. From negative 2 to 2, that's the rectangle minus the semicircle. And 8 minus 2 pi is going to roughly be around 8 minus 6, which is around 2. And we compare these y values here. Highest and lowest y value. Highest is 2, lowest is negative 1. We're asking for the absolute minimum, so the absolute minimum value is negative 1 when x equals to negative 4. Last part here. We have a differential equation for x is greater than 3. And we're asked to find a particular solution. So let's cross multiply, separate the variables, begin to start our process so we can take the antiderivative. So when I cross multiply, I get y dy is equal to h of x plus x squared dx. Let's make sure everything is set up where our variables are nicely separated. Y is on the left, everything else on the right. Take the antiderivative. This is just power rule. Now the right side, let's replace h of x with what we have above. For x is greater than 3, we're going to choose this last portion here. Okay. So we have to go through the antiderivative rules here. This is u substitution, that's power rule. Well, actually these two terms cancel out. 5 is also power rule. We go through u substitution, e to the u, let our u value be 2x minus 6. Derivative is 2. We solve for dx, which is du over 2. We make our substitutions. 4e to the u times du over 2. The 4 and 2 comes out to be just 2. And now we can find the antiderivative. 2e to the u is just 2e to the u. 5 becomes 5x. A plus c shows up, and the left side is y squared over 2. Right? once that plus c shows up, I'm going to take my order pair and see if I can use it to solve for c. So 4 plugs in for x, negative 2e plugs in for y. This becomes 4e squared over 2, which is just 2e squared, and everything else cleans up to be c is equal to negative 20. Now once I solve for c, I still have to go back and solve for y. So continue at the top of the page. I ran out of room here, so once I found the c value, I put it back in where I initially made the substitution, and then algebraically just want to try to get y by itself. So multiply both sides by 2, get that 2 to move over to the right side. And then once I'm down to y squared, I'm take the square root. So when I take the square root, I have plus or minus square root. And these are two separate solutions. We have to decide which one to choose. And the one that we know to choose is it has to fulfill this order pair for negative 2e. So we look at the y value. Whatever the sign of the y value is, it's going to help guide what sign we choose for our square root. All right, because if I plug 4 in, the only way I can get a negative 2e in return is if a negative is sitting outside. So r of x is negative square root of 4e to 2x minus 6 plus 10x minus 40.